Good afternoon, class. Here's exam 2 review covering chapters 3, differentiation rules. Here's part 4 covering section 3.6, derivatives of the logarithmic functions. So derivatives of the log functions, y equals ln x. How do we differentiate that? We have seen how to differentiate the exponential function, but not the logarithmic functions. So recall, when y is ln x, that means e to the power of y equals x. So that means e to the power of y equals x. And this, we know how to differentiate because e to the power of kx, the derivative itself is times k, e to the power of g of x is itself times g prime of x. And so now, implicit differentiation, remember y is like g of x. So if I want to differentiate this, I get e to the power of y itself times g prime times y prime or dy dx, and x gives me 1. So y prime is 1 divided by e to the power of y, which is x. In other words, in order to differentiate y equals ln x, all you have to do, flip over its argument. Therefore, the derivative of ln x is 1 over x. Now, why are we writing absolute value and x is not equal to 0? This is clear, x can't be 0 because you can divide by 0. Why is it absolute value? This has got to do with the domain of logs that is 0 to infinity. For example, here, we would write d dx of ln of g of x. According to this rule, 1 over g of x. And according to the chain rule, times g prime. When we write g of x larger than 0, it covers everything. D dx of ln u, remember u is like g of x, is 1 over u du dx, and u must be positive. To continue on that, I'm going to remind you of logarithmic properties because we're going to use them here. Log xb equals y. Look at this arrow, means b to the power of y equals x. So for logarithmic properties, b must be positive and can't be 1. In that case, y equals log x base b is equivalent to x equals b to the power y. If you look at both, they have the same exponent y, the same base b. So for a general case, we get the following properties. And I put numbers there so we can go back and forth, refer to those. Log 1 base b equal to 0. And what it means is that if your argument is 1, regardless of the base, the answer is 0. Log b base b equals 1. That means if the base and the argument, the base is b, the argument is b. If they're identical, the answer is 1. Log base b of b to the power of x is x. And all those three can be found easily by looking at the arrow here. B to the power of 0 is 1. B to the power of 1 is b. B to the power of x is x. Also, these two refer to the fact that logarithmic functions and exponential functions are inverse of each other. This is b to the power of log x base b equals x. They undo each other. Product rule, quotient rule, power rule. Log xy is log x plus log y. All of them have the same base b. Log of x over y is log x minus log y. All of them have the same base b. And log of x to the power of n is n log x. In other words, n becomes the coefficients as long as we have the same base b. Now, when the base is 10, we call it common log and we don't write the base. So y equals log x or log x, that means the base is 10. And by exponential rule would be 10 to the power of y equals x. And these are the rules. Now, to understand those rules, basically numbers 1, 5, 6, and 7, you drop the base b, that's all. But as an example, if you look at number 2, if the base is b and the argument is b, the answer is 1. When you have log, that means the base is 10, so log 10 becomes 1, and the rest of them follow in the same manner. When the base is e, log x base e, we don't write it like that. We use ln. So y equals ln x, means the base is e, and these are the properties now. Again, numbers 1, 5, 6, 7. Drop the log and make it ln. That's all. Drop the log and the base and make it ln. But for example, number 2. Number 2 again says the argument is b, the base is b. This one, ln, that means the base is e, so the argument must be e equals 1, and so on and so forth. You got to be comfortable with logarithmic properties to be able to handle this section. So having said that, because exponentials and logarithmic functions are inverse of each other, if you graph them on the same set of axes, they are symmetric with respect to the line y equals x. Now notice, this point refers to the x-intercept. And if x is between 0 and 1, ln is negative. If x is larger than 1, natural log is positive. The y is positive. That means this one. So pretty straightforward. We also have the change of base formula, log x base b equals log x over log b. Choose any base, for example, a. But we would choose either common log or natural. And again, as far as differentiation, a derivative of ln x is 1 over x. The derivative of ln of g of x is 1 over g of x times g prime. This is by the chain rule. And if you happen to have a base other than e, we also need 1 over ln b. For example, the derivative of log f of x base b equals 1 over f of x, flip it over, times f prime by the chain rule, times 1 over ln b by the logarithmic properties. All right, let's look at this example. We have y equals ln of sine theta, and we want to differentiate that. And all we have to do, follow this. So 1 over sine theta, you got to flip it over, and then times the derivative of sine, which is cosine. And as you know, cosine over sine is cotangent theta. Y equals e to the power of x over 1 minus e to the power of x. We use the quotient rule. We're going to write it as f over g. And we're going to use the quotient rule. F prime g minus g prime f over g squared. So f prime is e to the power of x times g, which is 1 minus e to the power of x, minus g prime. This doesn't give you anything. Minus e to the power of x is itself. So minus e to the power of x, and times f, which is e to the power of x. And just write the bottom in a parentheses and square it. And this is the extent of calculus. Let's distribute. We get e to the power of x here. This one minus e to the power of x times e to the power of x is e to the power of 2x. Negative, negative makes it positive. E to the power of 2x. And these two cancel each other. We get e to the power of x over 1 minus e to the power of x quantity squared, and we are done. What about y equals ln x cubed? There are two ways to do that. I'm going to do both ways. First of all, it is simple enough. You can deal with it just the way it is, which means number 1, flip it over. 1 over x cubed. And g prime times its derivative 3x squared. And it simplifies to 3 over x. However, we could use logarithmic properties, a more specific case, power rule, put number 3 in front, becomes 3 ln x, and now deal with that. As you know, the derivative would be 3 times, and ln x gives us 1 over x. We get 3 over x. By the way, we are assuming x is positive. I want you to know that. If we don't know, we have to go with the absolute value. So having said that, in this case, didn't make much of a difference because it was simple enough. But the more complicated the log, the better the second way. That means decompose the log first. I can't emphasize this enough. All right, we are going to move on. Y equals log base 3 of square root of x. So again, we dealt with the log, the natural log, and we proved what the derivative was. But if the base is not e, how do we deal with that? We are going to go with the change of base formula, write this as ln x over ln b. So this is the proof. In other words, 1 over ln b times ln x. 1 over ln b is a number. Some number times ln x. So the derivative is the same number times the derivative of ln x, which is 1 over x. And we combine them in this manner, everybody. So very straightforward. So we're going to do the same thing here. But first thing first, I'm going to change the square root of x to x to the power 1/2. And I'm going to use the power rule, number 7. Of log properties and put the 1/2 in front. And now I'm going to differentiate this. So 1/2 remains, y prime equals 1/2. And log, I'm going to flip this over and get 1 over x. Then the base is not e, so 1 over ln b, 1 over ln 3 because of the change of base formula. And we just rewrite it. What about this one? Reminding you that we are dealing with the same case, we tag along the chain rule. In other words, the derivative of log base b of f of x, you flip this over, 1 over f of x, times f prime by the chain rule. Since the base is not e, 1 over ln b, this is by the logarithmic properties, which is the change of base formula. Put them together. This one, first thing first, can I simplify using properties of logs? No, so flip it over. 1 over x squared plus. By the chain rule, I need the derivative of the argument to x. The base is e, no. So I need 1 over ln 5 by the change of base formula. Put them together, and we are done. All right, we're going to continue with differentiation. Y equals ln of 5x over x squared plus 5. You can do this in one shot, but just to remind you things we have learned. So this is ln. I'm going to look at the quotient rule. Ln of 5x, ln of the top minus ln of the bottom. Also, ln of the top 5x is ln using number 5. The product rule is ln of 5 plus ln of x. Now we're going to differentiate piece by piece. Ln 5 is a number, gives you 0. Ln x gives you 1 over x. So that's very straightforward. Minus. To differentiate this first, we're going to flip it over, 1 over x squared plus 5. And then by the chain rule, the derivative of the inside is 2x times 2x. And we are done right here with calculus. We are going to finish it off using our algebraic techniques, which means this is 1 over x. This is minus 2x over x squared plus 5. Therefore, the product of x and x squared plus 5 is our LCD, the least common denominator. So having said that, 1 times x squared plus 5 minus 2x times x. So 1 times x squared plus 5 minus 2x times x. And so we have x squared plus 5 minus 2x squared. And these two combine, the final answer would be minus x squared plus 5 over x times x squared plus 5. It's pretty straightforward, everybody. What about this case? Log of 9 minus x cubed to the power of 4. Well, to differentiate this, first we're going to use number 7 of logarithmic properties, which is known as the power rule. We put the 4 in front. And now we are going to differentiate this. G prime of x equals 4. Then we deal with log. We flip this over, 1 over 9 minus x cubed, the reciprocal of that. The chain rule, we need negative 3x squared. The base is not e. 1 over natural log of the base is 10. 1 over ln 10. And we just rewrite it. So what is in the numerator? 4 times 1 times negative 3x squared times 1, negative 12x squared. What is at the bottom? The product of these two. So the final answer, y prime is negative 12x squared, 9 minus x cubed, ln of 10. And you want to put this on the left side because if you put it here, one may think it's a part of the argument of the log, which is not true. Okay. Okay. To differentiate this, we're going to do the same thing. We're going to use the properties of logs. For this one, we're going to use number 6, the quotient rule. So we're going to keep the 1/2, and this becomes ln of the top, 1 plus x, minus ln of the bottom, 1 minus x. So that's algebraic technique. To differentiate this, we're going to say y prime equals, we keep the 1/2 in front of the brackets. We're going to work on this. This is 1 over 1 plus x times the derivative of the argument, which happened to be 1. It's not changing anything. This one is minus 1 over 1 minus x, and times the derivative by the chain rule. The derivative of the argument, the parenthesis 1 minus x, is negative 1, and it does make a difference. So notice, this doesn't change. This is just 1 over 1 plus x. But this one is negative 1 times negative 1. That means this thing changes to plus 1 over 1 minus x. Therefore, when we want to rewrite and take a common denominator, again, 1/2 remains. The common denominator would be 1 plus x times 1 minus x. This one, 1 times 1 minus x. Again, let me just do this. Class, this is the end of calculus step. This was algebra, this was algebra, this is going to be algebra from here on. So again, 1 times 1 minus x, it goes here. And then plus 1 times 1 plus x goes here. And all we have to do, simplify the top. The bottom is 1 plus x times 1 minus x, which is 1 minus x squared. What happens to the top? Let's write. We have a 1 minus x plus 1 plus x. Therefore, we have 2. 1/2 times 2, they cancel each other. We just get 1. The denominator, as I mentioned, the product of these two is 1 minus x squared. Therefore, y prime is 1 over 1 minus x squared, and we are done. Y equals ln of ln of 5x. To differentiate this and to make sure no one has any problem with that, I'm going to say, okay, this is g of x, everybody. So that means I need 1 over g of x, so 1 over ln of 5x. And then I need g prime. G prime. What is the derivative of ln of 5x? 1 over 5x times 5. So I hope you see what we've done here. Very straightforward, very simple. And to put this together, obviously, the 5 from the top and the bottom cancel each other. The numerator is just 1. The denominator is ln of 5x times x. We put the x in front, becomes 1 over x ln of 5x. Y equals x squared ln x, and we want to find the equation of a tangent line at 1, 0. So that means we need to find the slope because we have a pair. All we have to do differentiate first. To differentiate, we notice is x squared times ln x and sit there. So therefore f times g, the power, the product rule. We're going to use that. So having said that, f prime is 2x times g ln x. So f prime g. Now we have g prime f. G prime is 1 over x times f, which is x squared. So let me write at top of it f prime g plus g prime f. Now, this is 2x ln x. These two cancel each other. They give us just x. So this is not the slope. It's important to understand this is not the slope. When we plug in, then it becomes this slope. So having said that, let's replace the x with 1 and come up with the answer. So m is y prime of 1, which makes it 2 ln 2 times 1 times ln 1 plus 1. As you know, I didn't write 2 times, but it's just 2. Okay, that's just as good. So ln 1 is 0, so the answer is 1. Y minus y1 equals m times x minus x of 1. So y minus 0 is 1 times x minus 1. As you know, this just remains as 1. This is x minus 1. So y equals x minus 1 is the final answer, everybody. Differentiate y equals log base 3 of 1 plus theta ln 3, and bear in mind theta is the independent variable. So quickly, there are a couple of ways to approach that. Number one, as was mentioned, you're dealing with the log. First, you want to decompose it. We can't. So simply put, flip this over. 1 over this, 1 over 1 plus theta ln 3. times f prime. Now the derivative of this, 1 is 0. Remember, theta is like x. ln3 is a number. So the derivative of this is just ln3. And then we look at the base. Is the base e? We are done. It's not 1 over ln b, 1 over ln3, because the base is not e. So I hope that everybody is okay with that. So y prime is 1 over 1 plus theta ln3 is the final answer. Yeah, and just again reminding you of the change of base formula, meaning everybody, this is the same as natural log of the same thing over ln3. That's the change of base formula. We went over the proof of that with the change of base formula in case. All right, y equals natural log of 2 e to the power minus t sine t. We're not going to differentiate it yet. Instead, we are going to decompose the log and then take it from there. So this one uses the product rule. Number 5. ln of 2 plus ln of e to the power minus t plus ln of sine t. Now, before we move on to differentiation, I want to remind you, what is ln of e to the power minus t? What is ln of e to the power of x? X. So that one is minus t. Now we are going to differentiate piece by piece. ln2 is a number. The answer is 0. Minus t minus 1. ln of sine t, flip this over, plus 1 over sine t times the derivative of that cosine t, and of course cosine over sine is cotangent, so y prime is negative 1 plus cotangent t. This is the final answer. In other words, using logarithmic properties is extremely important, and understanding it makes a huge difference, everybody. So it's important to know what to use, what property to use, and when to use it. Okay. Y equals t log base 3 of e to the power of sine t ln 3, and we want to differentiate that. So first and foremost, we are going to use our techniques of logarithmic properties, reminding you ln of e to the power of x is x, e to the power of ln x is x, and we notice that this has e ln to the power of 3, so we can put this first. Take a look at what we do. So t log base 3, and this one, we are going to write e to the power of ln 3 to the power of sine t. Please understand, I'm not changing anything. The nature of the argument of log is intact. It's not changed. So e to the power of ln 3 sine t is the same as e to the power of sine t times ln 3, because it's the product of ln 3 and sine t. However, according to this, e to the power of ln x is x, e to the power of ln 3 must be 3. Also, I'm going to bold the base here. So log base 3 of 3 to the power of sine t, reminding you log base b of b to the power of x is x. So because these two are the same, just the answer is sine t. So t times sine t. So I hope you see we took a few steps to make it actually simplify. And now obviously you can use the product rule. F times g. So the derivative is f prime g, f prime is 1 times sine t, plus g prime, the derivative of sine is cosine t times f, which is t. So f prime, let's just write on top of it. So f prime g plus g prime f. And so sine t plus t cosine t would be the final answer. Y prime equals sine t plus t cosine t. Again, and I hope you see that on purpose. I'm changing the dy dt to y prime. Just want to make sure you understand that. You could say y prime. The advantage of dy dt is that you're telling your reader the independent variable is t. Okay? Logarithmic differentiation, when a function is involved, we use logarithmic differentiation. What is logarithmic differentiation? Number one, take natural log of both sides. So if I take the natural log of both sides, the left side is ln y. I'm going to decompose this. So I'm not going to take time, okay? Uh, too many steps. So ln of the top minus ln of the bottom. So ln of the top is ln of this piece plus ln of this piece minus ln of this piece. And this one I'm going to write it x squared plus 1 to the power 1/2. So ln of x to the power of 3/4 plus ln of square root of x squared plus 1, which is x squared plus 1 to the power 1/2, minus ln of 3x plus 2 to the power of 5, because it's in the denominator. Now each one, now this was the quotient rule. Now I'm going to use number 7 and put 3/4 in front, 1/2 in front, 5 in front. Okay. So that's the first thing we do. And now we are going to differentiate implicitly with respect to x. So if I differentiate this one, I get 1 over y times dy dx. So 1 over y times dy dx, or y prime. If I differentiate this, I get 3/4 times 1 over x. If I differentiate this, plus 1/2, flip this over, 1 over x squared plus 1, and times its derivative by the chain rule, 2x. Minus 5, flip this over, 1 over 3x plus 2, and by the chain rule, its derivative, number 3. Finally, solve for dy dx. How do you solve for dy dx? The right side times y. So put 1 over y to the right, that means multiply by y. So y times, this will be 3 over 4x. This will be 1 and 1, and x, just x at top over x squared plus 1. This will be minus 15 over 3x plus 2. And you must replace the y with what you had in the first place. This is the end of the story. As you can see, it's complicated enough. This, you don't have to combine. Sometimes they do, sometimes they don't. It's not a big deal. Okay, so logarithmic differentiation. When do we use that? Normally, they tell us when to use it, but we use it when the expression is very involved. Also, in this case, y equals x to the power of sine x, when the base as well as the exponent are both functions of x or t, functions of the independent variable, one methodology is logarithmic differentiation. There's a second method. I go over that in a moment too. But y equals x to the power of sine x. How do we differentiate it? We differentiate with logarithmic differentiation. That means number one, take natural log of both sides. So the left side is ln y. The right side, using number 7, I bring the sine x to the front, and now I'm going to differentiate implicitly. Ln y is 1 over y times y prime, and the right side, I use the product. So that's pretty straightforward, everybody. F prime g plus g prime f. F prime is obviously cosine x times g ln x, plus g prime is 1 over x times f is sine x. And therefore, we are ready to solve for dy dx of y prime, which means put 1 over y to the other side. How? Multiply it by y. If I multiply by y, this goes away. This becomes y prime. So I put the y here. This is cosine x ln x. This is 1 over x sine x. And I'm going to replace the y with the function x to the power of sine x. And this is my final answer. However, I can use the second method. Method 2, we know e to the power of ln x is x. So we can replace the x with that. So x to the power of sine x becomes e to the power of ln x times sine x. So let's just rewrite it as y equals e to the power of ln x times sine x. And if I want to differentiate that, how do I differentiate that? Exponential, the answer is itself. So you write itself times what? The derivative of ln x times sine x. This is exactly what we had. Ln x times sine x or sine x times ln x is the same thing. You go through the process, you get this one and you put it there. And this one is replaced with x to the power of sine x. So you don't have to do logarithmic differentiation, but anyways, you have to use logarithmic properties, one of them to do the math. Derivatives of inverse trigonometric functions, I'm going to give them to you, and I'm going to look at a couple of proofs. The derivative of sine inverse is 1 over square root of 1 minus x squared. The derivative of tan inverse is 1 over 1 plus x squared. The derivative of secant inverse is 1 over x squared of x squared minus 1. The rest of them are identical with negative signs. So for example, cosine inverse would be the same thing, becomes negative. So the derivative of cosine inverse is the same as this one, but negative 1, negative. So negative 1 over square root of 1 minus x squared. For cotangent inverse, the same thing. This one becomes negative, minus 1 over 1 plus x squared. And cosecant squared, cosecant inverse, you want to take the derivative, same thing as this one, minus 1 over x squared of x squared minus 1. Reminding you about the inverse functions. None of the trigonometric functions are one-to-one. They don't have an inverse unless you limit the domain, as you recall. So sine inverse of x equals y means sine y equals x, and y is between negative power 2 and power 2 because of the restriction we put on x in the first place to make it a one-to-one function. For sine, We put it from negative power 2 to power 2 for the x for it to have it. Therefore, sine inverse of sine x as well as sine of sine inverse of x become x as long as this x belongs to sine x. So x is between negative and positive power 2. This x belongs to sine inverse between negative 1 and 1. Same thing for the cosine. Cosine inverse of cosine x and cosine of cosine inverse of x, both of them are x. This one x belongs to cosine. I hope you remember the restriction was between 0 and pi. Okay. The first and the second quadrant. This one was the fourth and first quadrant. And in this case, x belongs to cosine inverse from negative 1 to 1. And so this is the synopsis of what we just wrote here. However, what I want to add, for example, this one. If I replace the x with the u, where u or g of x, please understand, when we write u, we mean g of x, we mean some function of x. Then this is u, but now we have du dx. So 1 is the derivative of x. But if it happened to be a function of x, we need its derivative, so du dx. Or tan inverse, for example, if you look at this one, we are going to have g prime over 1 plus g of x, quantity squared. Now, quickly, let's look at some of the proofs. So we have all of those. And sine inverse of x equals y, sine y is x, and y is between negative power 2 and power 2. And we want to differentiate sine inverse of x, and we want to prove that it's 1 over 1 minus x squared. We want to prove that. So to do this, we are going to start with sine inverse equals y, or y equals sine inverse. Then in order to differentiate that, we are going to rewrite this. By definition, sine y becomes x. And we know how to differentiate sine. We're going to do it implicitly because y is like g of x. So sine of g of x becomes cosine of g of x, g prime, or in this case, cosine y, dy dx. The right side is x, just 1. Therefore, dy dx is 1 over cosine y. It's very straightforward, everybody. And so if that is the case, what is cosine y? We know Pythagorean identity says sine squared and cosine squared, they add up to 1. Therefore, if sine y is x, cosine y must be square root of 1 minus sine squared y, and you replace it with x. This is by Pythagorean identity, everybody. And replace it, and the limit that we put on x, if you will, for it to have an inverse. The first and the fourth quadrant cosine is positive, by the way. So we have dy dx is 1 over cosine y, and we showed cosine y squared of 1 minus x squared. We're done. We proved the derivative of sine inverse is 1 over square root of 1 minus x squared. What about tangent? Tan inverse of x equals y. By definition, tan y equals x. And again, the limit that we put on tan is similar to x. It's sine, except the endpoints are not included. So we want to prove the derivative of tan inverse is 1 over 1 plus x squared. Therefore, we are going to differentiate this piece. Tan y, the derivative is secant squared. So secant squared y. And then y is like g of x times g prime of x, or dy dx, x becomes 1. Therefore, dy dx is 1 over secant squared y. All we have to do, find the relationship between the two. As you recall, again, one of the Pythagorean identities tells us that 1 plus tan squared is secant squared. So if secant squared y is 1 plus tan squared y, I can put 1 plus tan squared y. But tan of y is x. So 1 plus tan squared y must be 1 plus x squared. So I'm going to replace it. And that's a proof that the derivative of tan inverse of x is 1 over 1 plus x squared. I highly recommend you try cosine inverse, maybe cotangent inverse, maybe secant inverse. Try to prove that, and it will help you understand the concept better. Y is e to the power of 10x. Tan inverse of x. We want to differentiate this immediately. We recognize this as a product rule, and we put a raised dot in between. We call it fg, and we're going to go with the product rule. F prime. E to the power of 10x is itself times 10. That's f prime times g tan inverse. Plus tan inverse is 1 over 1 plus x squared. Times f e to the power of tan x. And I'm going to put an asterisk next to it again. Believe it or not, we're done with calculus. We are not finished, but we are done with calculus. So this one, we put the 10 in front. Okay. And this one, we put e to the power of 10x at top. You can leave it like that. You can even factor the e to the power of 10x out. This becomes 10 tan inverse of x. This becomes 1 over 1 plus x squared. It doesn't make much of a difference. Y equals cosecant inverse of e to the power of x. The purpose of that is if you ignore e to the power of x and imagine it's x, okay, then we are dealing with cosecant inverse, which is simply negative 1 over x squared of x squared minus 1. And we're done. But because it's a function, I want you to understand that basically now we go with the chain rule. So I want to write this negative 1 something square root of something squared minus 1. It's important to know when it's x, you put the same, you put the same thing here and then square it here. So e to the power of x, the same thing goes here, gets squared up here, and so that's where it comes from. And we need the g prime now because this is a function of x. So from here, it was the basic. From here, we are looking at g of x, and then g prime. What is the derivative of e to the power of x? E to the power of x. And these two cancel each other. dy dx becomes negative 1 over the square root of e to the power of x to the power of 2 is e to the power of 2x. So dy dx becomes negative 1 over the square root of e to the power of 2x minus 1. What about x? Y equals x sine inverse of 3x. Again, we put a raised dot and we go with the product rule, everybody. So f prime is 1 times g sine inverse of 3x plus g prime. Now, again, if you look at 1 over square root of 1 minus x squared, remember when it's x, you get it squared up, okay? So let's stick with that and let's put a, parenthesis here. So what this means here, this one, you have x squared. That means you put the same thing here. What means here? 1 is the derivative of x. So now you need the derivative of 3x. In other words, stick with that. 1 over square root of 1 minus gx times g prime of x, or g prime of x over square root of 1 minus g of x squared. So this one is 3x, and this one is derivative. So 3. And so this doesn't change. It's just sine inverse of 3x. Okay. And by the way, times x times f. So this is sine inverse of 3x. This one is 3x over the square root of 1 minus 9x squared. What about y equals x cosine inverse of x minus the square root of 1 minus x squared? Well, this one is using the product rule, everybody. That's why we put a raised dot and then fg. And this one, we're going to write it 1 minus x squared to the power of 1/2, so we can use the extended power rule on that. So stick with this. F prime g plus g prime f. f prime is 1 times cosine inverse of x plus cosine inverse of x, negative 1 over square root of 1 minus x squared, plus negative 1 over square root of 1 minus x squared times f, which is x. So that's done. Minus this one, 1/2. 1 minus x squared to the power of negative 1/2 because it's 1 minus 1/2. And then the derivative of the inside is negative 2x. Notice this one, we want to rewrite this. Please understand, you have 1 over 2. This goes down, becomes positive 1/2, and therefore square root. Now, minus 2x sticks at top. Okay, so again, this is 1 and minus 2x at top. 2 times 1 minus x with the power of positive 1/2. Okay, which is the square root. So first and foremost, 2 and 2 cancel each other. So let's go here. We have cosine inverse of x minus x over square root of 1 minus x squared, negative, negative, positive. And remember, number 2 cancels out, gives us just negative x at top. Negative times negative gives us positive x at top. And I hope you recognize that these two are opposites, and therefore the final answer, dy dx, is cosine inverse of x.